Hello everyone, my name is Rinku Shah. I am a final year PhD student at IIT Bombay. Today, I will present a work titled TurboEPC, Leveraging Network Programmability to Accelerate the Mobile Packet Core. New telecom use cases like the IoT, industrial automation, and virtual reality require ultra-low latencies for data plane as well as control plane, extremely high data rates, and should be able to cater densely populated regions. Mobile network providers should provide required user scalability and performance. We take small steps towards this goal and present a new architecture for the 4G Evolved Packet Core EPC. I will first give an overview on the mobile packet core. In a typical cellular network, the mobile users connect to the base station and multiple such base stations connect to a single mobile packet core. The control plane of the packet core processes the 4G EPC signaling messages, and the data plane simply forwards the data to and fro the internet. Traditionally, the mobile packet core was built as custom hardware appliances that perform specific functions. This figure shows the basic components, the mobility management entity MME, the home subscriber server HSS, and the service and packet gateways SGW and PGW. Now I'll talk about few signaling messages that the mobile core processes. The user generates an attached message to register to the network. For attached message processing, the MME performs user authentication using the security key database HSS, whereas the gateways set up data sessions and configure data plane rules. If the user is idle for a few seconds, S1 release message is invoked, which deactivates the data channel. Service request message activates the data channel when the user or network wants to send data. Handover messages are used to manage the user's connection on the move. And lastly, detached message is used to deregister the user from the network. Traditional custom hardware appliances have long turnaround times for packet processing modifications. Hence, this architecture is not flexible. The solution is softwareization of the control plane. Towards control plane softwareization, the telecom community has embraced software-defined networking paradigm and calls this SDN-based architecture as CUPS, where the control plane is separated from the data plane hardware and the control plane logic runs on SDN controllers over commodity servers. The CUPS-based architecture improves the flexibility and eases management and configurations. But the SDN control plane scalability is a known challenge. Also, the 4G control plane is unable to meet the throughput and latency demands of exponentially growing mobile users. Next, we see how the research community addresses the scalability challenge. Proposals like Scale use horizontal scaling approach and a tightly coupled design to scale the control plane. Proposals like Pepsi refactor the EPC state to reduce inter-procedure communications and hence improve throughput. Proposals like DPCM modifies the number of messages exchanged in the EPC protocol to scale and speed up. All these proposals provide acceleration solutions at the mobile packet core, which is a few tens of milliseconds away from the user. Few proposals distribute the control plane of the packet core to the local controllers close to the user. Our proposal TurboEPC takes one more step close to the user by offloading the control plane functions to the data plane switch close to the user. TurboEPC grabs the opportunity of utilizing the spare data plane CPU of typically oversubscribed switches on the path towards the core. The load is reduced at the core network, and the end-to-end latency reduces significantly as the control packets are processed at the switch hardware close to the user. Our key idea is to offload subset of mobile core processing to the edge at the programmable hardware switches. The programmable switch hardware allows a programmer to specify the packet header formats, the packet parsing algorithm, and the life cycle of any packet. I shall now describe the architecture of TurboEPC. Some of the functions of MME, SGW, and PGW are offloaded to the programmable edge switch. Few signaling messages are processed at the edge switch, and response messages are sent from the switch itself. These messages never travel to the core network. We term these signaling messages as offloadable messages, and the rest are called non-offloadable messages. I will now describe the processing of non-offloadable messages. We have classified attach, detach, and handover as non-offloadable messages. How did we decide this? I'll come to it in a bit. An attach message is processed at the mobile packet core where the user context is created. This user context is then cached at the edge switch for later usage by offloadable messages. We have classified service request and S1 release as offloadable messages. S1 release message is processed at the edge switch, and the user context is updated at the switch to indicate that the user is idle. In the next few slides, I will talk about TurboEPC challenges and their respective solutions. Our first challenge is to decide that which of the EPC signaling messages can be offloaded. In order to answer this question, we first classify the EPC state as offloadable and non-offloadable. EPC state is offloadable if it is either local to the switch or it has session-wide scope. That is, the state is temporary and the state is not accessed concurrently from multiple network locations. For example, the user connection state is updated by the user during S1 release and service request processing. This state is valid for a session and the user can be present at a single location at any point of time. An EPC state is non-offloadable if it is global and has network-wide scope. This state can be accessed from multiple locations concurrently. The security key stored in the HSS database is a good example of global state. So to answer this question about which of the EPC signaling messages can be offloaded, we state that if all the states accessed by the message are offloadable, then the message is offloadable. This table shows the EPC signaling messages and the states accessed by them. The service request message updates the user connection state to active, updates the forwarding state and subscriber identifiers. We notice that both service request and S1 release do not access non-offloadable state, and they are probable candidates for offload. This slide shows the guide to classify messages. An EPC message is a good offload candidate if all the states accessed are offloadable. We saw in the previous slide that service request and S1 release satisfy this condition. The message spans a significant fraction of total traffic. Else, the effort of offload itself is wasted. The pie chart shows the EPC traffic distribution, and we see that S1 release and service request comprise of more than 90% of total traffic. So they satisfy the second condition. Third, we should be able to write the code for message on the programmable switch target. Also, the offloaded state should not be accessed frequently by non-offloadable messages. Why? I'll talk about this in a bit. To conclude, TurboEPC offloads S1 release and service request messages to the edge programmable switch as they satisfy all the conditions. Our next challenge is to ensure consistency of offloaded state. If a non-offloadable message like handover needs to access offloaded state, offloadable message could have modified the state at the edge switch, and this offloaded state could be stale at the mobile packet core. So the naive solution is to sync the state from the switch to the controller. But this is expensive and negates the benefit of offload. Hence, the message offload guide mentioned the condition that the offloadable state should not be accessed frequently by non-offloadable message. TurboEPC's solution is to synchronize the state on demand. For example, the user is moving from the location of the source base station towards the target base station. The handover request arrives at the source base station and traverses to the core via the edge switch. The switch looks up for the offloadable user context and piggybacks this context with the packet before forwarding it to the core. The controller updates the user context at the core and marks the switch state as invalid. After the handover message processing is completed, the new state is pushed at the switch at the new location. State synchronization adds processing overhead. But since handovers comprise of only 4 to 5% of total signaling traffic, this overhead is acceptable. Note that the core should not offload processing for users with high handover rates. Our next challenge is that a programmable hardware switch has limited amount of memory. TurboEPC requires 96 bytes to store state for one user. Programmable hardware like Metronome can store state for 65K users, whereas Tofino switches can store state for few hundred K users. But a typical mobile network has few millions of users. The solution is to offload the state for a subset of users or add more switches to store the user state. TurboEPC uses the second solution. The details are present in our paper. Next, I present TurboEPC implementation for the edge programmable switch. We program the TurboEPC switch to process offloadable messages at the switch. We write the code in P4 language. This code is then compiled to generate custom packet pipeline and initial switch configuration. The compiled code is then pushed to the programmable switch. Now our switch is ready for processing EPC messages. When a user I sends an attached message, the message is processed by the core. The offloadable state is then cached on the switch using the P4 table and P4 register array data structures. The P4 table stores the user state as key value pair, where key is the user ID and value is the pointer to the register array, where the user state is stored. We use this indirect approach because table values are updated by the slow control plane. whereas register values can be updated within the fast data plane. So the table value is used as a static index to the register array where the user state is stored. Once the attach process is done, the reply is sent back to the user from the core. Later, when a user I's S1 release or service request message arrives at the switch, the packet pipeline performs read and write operations within the data plane itself, modifies the user context, and generates the corresponding response message. We now see the TurboEPC setup for both hardware and software prototype. A centralized control plane runs an ONOS controller for the software prototype and Python controller for the hardware prototype. The base station, the edge switch, and the core PGW switches are BMV2 switches for the software prototype and Netronom's 10 gig SmartNICs for the hardware prototype. The load generator is a multi-threaded C++ program that can generate traffic with different distributions for multiple users. We evaluate the performance of the centralized CUPS-based EPC with TurboEPC that offloads subset of control plane processing to the edge programmable switches. A first experiment compares the performance of CUPS-based EPC with TurboEPC software prototype. We vary the traffic mix and obtain the throughput and latency results. The x-axis is the traffic mix where ATT1 means 1% traffic is attached and the rest is offloadable. The typical traffic distribution is shown in the table. These TurboEPC results are for a single edge switch. The left graph shows the throughput for a single switch. And we see that TurboEPC has 1.3x improvement for attach 1 mix and 2.3x improvement for typical traffic. But as the non-offloadable component in the traffic mix increases, as we can see in attach 50, the throughput decreases. This is due to the high synchronization, state synchronization costs. Note that the typical traffic distribution does not have high non-offloadable component. The latency graph on the right shows that TurboEPC reduces latency by 70% for attach 1 and 90% for typical traffic. Also, TurboEPC scales to 5x with 4 edge switches and can scale further with more edge switches since there is 80% spare CPU at the core. In this experiment, we observe the TurboEPC hardware switch performance and also observe the impact of interfering data traffic on the EPC performance. In this graph, the x-axis is the data rate, which varies from idle condition to line rate, which is 8 Gbps in our case. The y1 axis shows the throughput, and the y2 axis shows the end-to-end latency in microseconds. Due to data interference, the throughput drops from 52K to 12K. And the latency increases from 100 microseconds to 180 microseconds. But even at line rate data interference, TurboEPC performs better than CUPS-based EPC. TurboEPC shows throughput improvements between 22x for line rate data and 102x for idle switch. And the latency reduction ranges between 97 to 98%. To summarize, we revisit the boundary between the control and data planes in the mobile packet core. TurboEPC shows significant improvements in throughput and latency. And this idea extends to the future 5G core. With this, I end my talk. Thank you for your attention.